How big is our neighborhood? Tonight, we're going to explore the true scale of our solar system. You've probably heard these measurements thousands of times. Distances in millions of kilometers, planets that are gas giants, asteroids floating in belts, between worlds. But here's what most people don't realize. The solar system isn't just big. It's big in a way that completely breaks how our minds process space and distance. By the end of this journey, you're going to understand exactly why even our own cosmic backyard transcends everything our brains evolved to comprehend. Before we dive in, if you enjoy these kinds of explorations, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Get comfortable. Let's begin. Physical reality starts in dimensions so small they completely defy human perception and our everyday experience. Think about the smallest thing you can imagine. A grain of sand, the tip of a needle. You're not even close. We need to go deeper, much deeper. At the foundation of everything you see, touch, and experience are particles called quarks. These fundamental building blocks measure approximately 10 to the minus 18th meters across. To put this in perspective, if a quark were scaled up to the size of a basketball, that basketball would be as large compared to our entire solar system as the quark is to the basketball. Your mind just hit a wall, didn't it? It's supposed to. Our brains simply didn't evolve to process numbers like this. 3 of these impossibly tiny quarks cluster together to form protons and neutrons, which occupy about 10 to the minus 15th meters of space. Still unimaginably small. Still beyond any direct experience you've ever had. Now here's where things get strange in a way that challenges everything you think you know about solid matter. The nucleus of an atom, made of these protons and neutrons, concentrates 99.9% of an atom's mass into just 1 femtometer cubed of space. Imagine the nucleus as a pea sitting in the center of a football stadium. The electrons? They'd be orbiting somewhere up in the bleachers. The space between them is just empty. Individual atoms measure between 0.1 and 0.5 nanometers across, approximately 10 million times smaller than the head of a pin. And here's the thing that should make you pause and really think about what I'm telling you. The solid matter you touch every single day, the chair you're sitting in, the phone in your hand, your own body, all of it is 99.999% empty space between these tiny particles. If we could somehow remove all the empty space from the atoms that make up every human being who has ever lived, all 8 billion people currently on Earth, plus every human throughout history, the actual matter would fit inside a cube of sugar. Let that settle in for a moment. We're made of almost nothing, floating in structures of almost nothing, creating an illusion of solidity that feels absolutely real to us, but is fundamentally an illusion. Even something as simple as a water molecule contains just 3 atoms, arranged at precisely 104.5 degrees between their bonds. Your DNA, when uncoiled, stretches up to 6.5 feet long but remains only 2 nanometers wide. That's like a thread so thin that if it were the width of a human hair, it would stretch from New York to Los Angeles. A typical human cell measures between 10 and 100 micrometers, finally reaching a scale visible under a decent microscope. Your body contains approximately 37 trillion of these cells, each one operating as an independent biochemical factory of staggering complexity. Bacteria living inside you and around you measure between 0.5 micrometer and 5 micrometers. Thousands of them could fit on the tip of a pin. Viruses are even smaller, between 20 and 300 nanometers, existing at the blurry boundary between life and chemistry. 1 millimeter represents the first scale where your naked eye can detect objects without any help from instruments. This is where human perception truly begins. Ants operate in this realm. measuring between about 0.04 of an inch and half an inch, living in a world where surface tension dominates gravity. Pour water on a table and watch an ant walk across it. You're seeing physics that doesn't apply to us. Your hand spans about 7 to 8 inches, establishing our first direct bodily reference. An average adult human stands about 5.5 feet tall, defining our natural perceptual scale, the center point from which we measure everything else. Cars typically stretch 15 to 16 feet long, roughly 3 times human height. This is still within our intuitive grasp. We can walk around a car, judge its size, understand it viscerally. But now we start reaching the edges of human-scale intuition. Small asteroids, just a few yards across, tumble through space between planets, rocky fragments, lost in the vast emptiness. An asteroid 33 feet in diameter contains about 1,500 tons of mass, equivalent to 15 full city buses. The asteroid that exploded over Chelyabinsk, Russia, in 2013 measured only 66 feet across before hitting our atmosphere. That explosion released energy equivalent to 500,000 tons of TNT, 30 times the Hiroshima bomb, just from friction with our air. 10-story apartment buildings reach about 100 to 115 feet high, roughly 10 times human height. Still comprehensible. You can look up at one and grasp its scale. But asteroids between 160 and 330 feet across number in the thousands, passing near Earth annually, most undetected until they've already gone by. The Burj Khalifa, humanity's tallest structure, reaches 2,700 feet, about 500 times average human height. Even this pushes the limits of what feels intuitive when you're standing at its base, looking up. Asteroids measuring hundreds of yards exist by the thousands throughout space, each one potentially devastating if it collided with Earth. An impact from an asteroid just 0.6 of a mile across would cause regional devastation equivalent to 50 million tons of concentrated explosive energy. Manhattan Island stretches 13 miles long, establishing an urban scale most people find familiar. New York City from coast to coast spans about 34 miles. This progression from atoms to cities covers a range of 1 to 10 million in relative size, approximately 7 orders of magnitude. Each order of magnitude means multiplying by 10. Going from 1 foot to 10 feet to 100 feet to 1,000 feet, each step multiplies the previous size by 10, but we're just getting started. The real journey into incomprehensible scale is about to begin. The Australian continent measures roughly 2,500 miles across from west to east coast. Pluto, that distant dwarf planet at the edge of our solar system, has a diameter of 1,477 miles, more than 1,000 miles smaller than Australia's width. This means Pluto, an object orbiting at the very frontier of our solar system, would fit comfortably inside the Australian continent with room to spare. Mount Everest rises 29,035 feet above sea level. The Himalayan mountain range extends more than 1,500 miles across Asia. The Grand Canyon carves nearly 6,000 feet deep and 277 miles long into the North American crust. Deimos, the smaller moon of Mars, measures just 7.5 miles across, probably an asteroid captured by Martian gravity billions of years ago. Its gravity is so weak that you could literally jump to space with a strong leap. Phobos, Mars's larger moon, spans 14 miles but orbits so close to Mars that it's gradually falling, destined to crash into the planet in 50 million years. The nucleus of Halley's Comet measures only 9 miles across, but when it approaches the Sun, its gas tail stretches 62 million miles, 2/3 the distance from Earth to our star. That tail becomes visible to your naked eye from 93 million miles away. Think about that for a moment. A 9-mile chunk of dirty ice creates a visible display spanning tens of millions of miles. We've now traveled through 27 orders of magnitude, from the smallest particles to objects you can see in the night sky. But this journey has only just begun. The true scale of our solar system and our cosmic neighborhood is about to reveal itself in ways that will challenge everything your brain thinks it understands about size and distance. And the most shocking discovery? Everything we've discussed so far, from quarks to comets, represents just the very beginning of a scale so vast that even our nearby cosmic neighborhood transcends all human comprehension. That tail equals 2/3 the distance from Earth to the Sun, visible to your naked eye when the comet approaches our planet. But comets are just the beginning of a collection of objects that will start stretching your mind toward breaking point. Let me introduce you to the asteroid belt and some of its more substantial residents. Asteroid 243 Ida stretches 35 miles long, approximately 3 times the length of Manhattan. But here's what makes Ida truly remarkable. It has its own tiny moon called Dactyl, less than a mile across. This was the first asteroid we ever discovered with its own natural satellite. Think about that for a moment. A 35-mile chunk of rock drifting in space captured an even smaller chunk to orbit around it. Gravity working on scales that seem almost quaint now, but were revolutionary when we first discovered them. This discovery fundamentally changed how we think about gravitational relationships in space. We'd assumed that only planets could have moons. But here was proof that even relatively small chunks of rock and metal could accumulate enough gravitational influence to hold their own satellites. Ida and Dactyl danced through space together, a binary system so small that both objects could fit comfortably inside most major metropolitan areas. As asteroids grow to hundreds of miles across, they accumulate enough gravity to gradually shape themselves into approximately spherical forms. These aren't the irregular potato-shaped rocks of smaller asteroids. These are miniature worlds with their own gravitational personalities, their own geological histories, their own stories written in impact craters and mineral compositions. The transition from irregular chunks to rounded worlds happens gradually. Asteroids a few dozen miles across remain lumpy and misshapen, but somewhere around the 100-mile mark, gravity begins winning its eternal war against structural irregularity. The asteroid's own mass starts pulling itself into a more efficient shape. The sphere, Enceladus, one of Saturn's moons, measures 313 miles in diameter. On its own, that's impressive enough, larger than many asteroids. But Enceladus does something extraordinary. It shoots geysers of water 124 miles high into space. These aren't small fountains. Picture water shooting up from the surface with enough force to reach an altitude equivalent to the distance from New York City to Albany. These geysers emerge from a subsurface ocean heated by gravitational tidal forces, making Enceladus a prime candidate for microscopic extraterrestrial life. The mechanics behind these geysers reveal something profound about the hidden energy sources in our solar system. Saturn's immense gravitational field constantly flexes Enceladus as it orbits, like someone repeatedly bending a piece of metal until it gets hot. This tidal heating keeps an ocean liquid beneath the moon's frozen surface, an ocean that might have existed for billions of years. Scientists estimate this hidden ocean contains more water than Lake Superior. Imagine that. A moon smaller than the state of Texas harbors an ocean larger than one of Earth's Great Lakes, locked beneath miles of ice, heated by the gravitational massage of a giant planet hundreds of millions of miles from the Sun. Vesta, the third largest asteroid, spans 326 miles in diameter, roughly 10 times Manhattan's length in every direction. Its surface gravity is just 2.5% of Earth's, meaning you could jump 131 feet high with a normal human leap. Imagine that. one decent push off the ground, and you'd soar 13 stories into the air before gently floating back down. Walking on Vesta would feel like moving through a dream where physics operates under different rules. Each step would launch you dozens of feet forward. A gentle hop would send you sailing in slow-motion arcs that would take long seconds to complete. The horizon would curve away visibly in all directions, reminding you constantly that you're standing on a world so small you could walk around it in a few weeks. Vesta bears a gigantic impact crater, 311 miles across, nearly the full width of the asteroid itself. This collision, which occurred billions of years ago, almost destroyed Vesta entirely. The fact that it survived speaks to the incredible violence that shaped our early solar system. The impact that created this massive crater was so violent it blasted chunks of Vesta completely into space. Some of those fragments eventually found their way to Earth as meteorites. When you see a meteorite in a museum labeled as being from Vesta, you're looking at a piece of rock that was literally blasted off an asteroid by an impact so powerful it nearly shattered a 300-mile-wide world. The early solar system was a cosmic shooting gallery. Impacts that would end civilization on Earth were routine occurrences. The largest planets and moons we see today are the survivors, the objects that endured this period of cosmic bombardment and emerged battered but intact. But Vesta is dwarfed by Ceres, the largest object in the asteroid belt. Ceres measures 588 miles in diameter and earned classification as a dwarf planet in 2006. Ceres represents a watershed moment in our understanding of solar system classification. When the International Astronomical Union redefined planetary categories, Ceres joined Pluto in a new class, dwarf planets. These objects are large enough for gravity to pull them into roughly spherical shapes, but not massive enough to clear their orbital neighborhoods of other objects. Ceres contains approximately one-third of the entire asteroid belt's mass, about 940 trillion tons. To put this in perspective, if every asteroid in the belt were somehow melted together into a single object, it would still be smaller than our moon and contain only 4% of the moon's mass. That's worth pausing over. The entire asteroid belt, millions of objects spread across hundreds of millions of miles, contains less material than 4% of our moon. This revelation fundamentally changed how astronomers think about planetary formation. The asteroid belt isn't a failed planet, as early theories suggested. It's a region where Jupiter's gravitational influence prevented a planet from forming in the first place. The giant planet's gravity stirred up the region so violently that rocky debris could never accumulate into anything larger than Ceres. Ceres might contain more frozen fresh water than all the liquid fresh water currently available on Earth. This water remains trapped beneath a frozen crust 25 miles thick, never exposed directly to sunlight. Recent observations suggest this subsurface ocean might still be liquid in some regions, making Ceres another potential harbor for primitive life. The possibility that multiple worlds in our solar system harbor hidden oceans represents one of the most exciting developments in modern astronomy. Europa, Enceladus, Titan, and now possibly Ceres, each hiding vast reservoirs of liquid water beneath frozen surfaces. We once thought Earth was unique in having liquid water. Now we're discovering it might be common, hidden just beneath the surface of worlds we previously considered dead. The asteroid belt extends between 2.2 and 3.2 astronomical units from the Sun, the region between Mars and Jupiter. 1 astronomical unit equals 93 million miles, the average Earth-Sun distance that astronomers use as their standard reference. Despite containing millions of asteroids, the space between them typically measures millions of miles of absolute void. The distance between two typical asteroids in the main belt averages about 1.2 million miles of separation. If each asteroid were a person standing upright, they'd be separated by distances equivalent to 5 round trips from Earth to the Moon. The total volume of the asteroid belt is approximately 16 trillion times larger than the volume of all the asteroids combined. Here's where our minds start struggling with the concept of emptiness on cosmic scales. You might picture the asteroid belt as a dense region packed with rocks. In reality, it's mostly empty space with occasional rocky islands separated by distances that dwarf anything we experience on Earth. The space between asteroids is more empty than any vacuum we can create in terrestrial laboratories. Hollywood movies showing spacecraft navigating dense asteroid fields, dodging rocks every few seconds? Pure fiction. Spacecraft traverse the belt regularly without any collision risk. The belt is mostly empty space punctuated by occasional rocks, separated by continental distances. NASA's mission planners don't even consider asteroid collisions when routing spacecraft through the belt. The chance of accidentally hitting an asteroid is vanishingly small, roughly equivalent to throwing a dart blindfolded and hitting a specific needle in a haystack the size of Texas. The Dawn spacecraft orbited both Vesta and Ceres between 2011 and 2018, mapping their surfaces in unprecedented detail. These images revealed impact craters billions of years old, mountains 12.5 miles high, and possible subsurface oceans. Dawn's mission represented a remarkable achievement in space exploration. Using ion propulsion, a technology that sounds like science fiction but works by accelerating charged particles, the spacecraft visited 2 different worlds in the asteroid belt. The gentle but continuous thrust of ion engines allowed Dawn to rendezvous with Vesta, study it for over a year, then depart for Ceres. The detailed maps Dawn created revealed these worlds as complex, geologically diverse places with their own unique histories. Vesta showed evidence of volcanic activity in its distant past. Ceres displayed mysterious bright spots that turned out to be salt deposits, evidence of the subsurface ocean that occasionally breaks through to the surface. Scientists estimate that 1.9 million asteroids larger than 0.6 of a mile exist in the main belt between Mars and Jupiter. Each of these minor worlds possesses unique craters, distinct chemical composition, and billions of years of evolutionary history. Every one of these nearly 2 million asteroids tells a different story. Some are metallic, the cores of larger objects that were shattered by impacts. Others are rocky, resembling the building blocks from which planets formed. Still others are carbonaceous, containing organic compounds and water that might have seeded early Earth with the ingredients for life. A typical asteroid 6 miles across contains sufficient mineral resources to supply the global economy for decades. The private company Planetary Resources estimated that nearby asteroids contain platinum and rare metals worth $100 trillion. The economics are staggering. A single metallic asteroid could contain more platinum than has ever been mined on Earth, more gold than exists in all terrestrial reserves, more rare Earth elements than we'll need for centuries of technological development. But there's a catch. However, reaching, mining, and returning materials from these bodies remains technically impossible with current commercially available technology. The Japanese Hayabusa 2 probe returned samples from asteroid Ryugu in 2020 after a 6-year round trip. Those samples weighed only 0.2 ounces, but contain primitive organic compounds that help scientists understand the origins of life, how the first single-celled bacteria formed on primordial Earth. 0.2 of an ounce. After 6 years of travel and billions of dollars in engineering, we retrieved less material than fits in a small test tube. Yet those microscopic grains contain information about the birth of our solar system, chemical signatures preserved unchanged for 4.6 billion years. Small solar system bodies preserved the original chemistry of the solar nebula, frozen in time for 4.6 billion years. These are fossils of our cosmic birth, unchanged witnesses to the formation of everything around us. But now we enter a realm where the objects themselves become worlds in their own right, where distances stretch beyond anything we can truly comprehend, and where the very concept of neighborhood begins to lose all meaning. Let me introduce you to Triton, Neptune's largest moon. This world measures 1,681 miles in diameter, orbiting in retrograde direction around the gas giant. That retrograde orbit, moving opposite to Neptune's rotation, provides crucial evidence that Triton wasn't born where we find it today. This is a captured object from the Kuiper Belt, gravitationally kidnapped billions of years ago when it wandered too close to Neptune's influence. Imagine the cosmic violence of that capture event. A world over 1,600 miles across, traveling at tremendous speed through the outer solar system, suddenly yanked into orbit around a planet 8 times more massive than Earth. The gravitational forces involved would have been catastrophic, likely reshaping both bodies and ejecting any other moons that might have existed in the Neptune system. Triton shoots geysers of liquid nitrogen 5 miles high into its thin atmosphere. Picture that, fountains of liquid nitrogen, a substance so cold it would instantly freeze any earthly material it touched, erupting with enough force to reach altitudes equivalent to commercial airliner cruising height. The energy source for these geysers remains partly mysterious. Triton orbits so far from the Sun that solar heating provides virtually no energy. The geysers likely result from a combination of internal heat and seasonal temperature variations that occur over Neptune's 84-year-long seasons. Europa, Jupiter's 4th largest moon, measures 1,940 miles in diameter, slightly smaller than our Earth's moon. But Europa harbors one of the solar system's most tantalizing secrets, a global ocean 62 miles deep beneath an ice crust 9 to 15 miles thick. That hidden ocean contains twice as much water as all of Earth's oceans combined. A staggering thought that should make you pause and consider what we might be missing in our search for life. The implications are profound. While we've spent centuries assuming Earth was unique in harboring vast oceans of liquid water, Europa has been hiding a larger ocean system right here in our solar system. That ocean has existed for potentially billions of years, warmed by tidal heating from Jupiter's immense gravitational field. Europa's icy surface is one of the smoothest in the solar system, with no mountains higher than 330 feet. This smoothness suggests the surface is geologically young, constantly renewed by water welling up from below and refreezing. The ice crust floats on the ocean like a planetary ice sheet, cracking and reforming as tidal forces flex the moon. Picture this hidden world, an ocean deeper than Earth's deepest trenches, locked beneath miles of ice, potentially harboring life forms that evolved in eternal darkness, warmed by the gravitational energy of the largest planet in our solar system. Our own moon measures 2,159 miles in diameter, a ranking as the 5th largest moon in the entire solar system. Proportionally, our moon is exceptional, measuring 27% of Earth's diameter, making it the largest moon relative to its parent planet. The moon's mass represents 1.23% of Earth's mass, a proportion that's extraordinary compared to other planet-moon systems we observe throughout the solar system. Most planets either have tiny moons that are clearly captured asteroids or, like Jupiter and Saturn, collections of many moons that formed from debris disks. The prevailing theory suggests our moon formed 4.5 billion years ago when a Mars-sized protoplanet collided with primordial Earth. This giant impact ejected molten material that condensed in orbit, coalescing into the moon within just 100 million years. Try to visualize that collision. a planet roughly the size of Mars, traveling at thousands of miles per hour, slamming into early Earth with enough energy to vaporize rock and eject material completely into space. The impact was so violent, it likely melted both objects entirely, creating a magma ocean on Earth and a ring of molten debris that eventually became our moon. The moon recedes from Earth at a rate of 1.5 inches per year, measured precisely by laser reflectors left by Apollo missions. 4 billion years ago, the moon was 20 times closer than today, dominating Earth's sky like a gigantic, threatening disk. In that ancient epoch, Earth's days lasted only 6 hours. The planet spun much faster, gradually slowed by the moon's gravitational braking effect over billions of years. Earth and moon were locked in a much more intimate gravitational dance, with tidal forces far more extreme than anything we experience today. The moon's tidal force currently raises Earth's oceans by up to 6.5 feet during spring tides. Without the moon, Earth's rotational axis would oscillate chaotically, preventing the stable seasons essential for complex life. Our moon doesn't just light up the night sky, it stabilizes the very climate that allowed life to evolve. Lunar surface gravity is just 16.5% of Earth's gravity, completely altering physical experience. The 12 Apollo astronauts who walked on the lunar surface between 1969 and 1972 remain the most distant human explorers in history. The moon orbits at an average distance of 238,855 miles from Earth, approximately 30 Earth diameters of separation. Light takes 1.28 seconds to travel from Earth to the moon, making this the first astronomical distance measurable with ordinary stopwatches. This distance, nearly 250,000 miles, represents a crucial threshold in human understanding of space. It's the farthest we've ever physically traveled, yet it's practically next door compared to the scales we're approaching. Io, Jupiter's innermost major moon, measures 2,264 miles in diameter and ranks as the most geologically active body in the entire solar system. More than 400 active volcanoes cover Io's surface, ejecting sulfur plumes 186 miles high constantly. The volcanic activity results from tidal heating caused by Jupiter's overwhelming gravitational pull. Io completes an orbit around Jupiter in just 42 hours, suffering extreme gravitational flexing that keeps its interior molten. The moon is literally being kneaded by Jupiter's gravity like dough in cosmic hands. Imagine standing on Io's surface, if you could survive the radiation and toxic atmosphere. The ground beneath your feet would be in constant motion, flexed by gravitational forces powerful enough to keep rock molten. Volcanic eruptions would be visible in every direction, painting the sky with sulfur compounds. Callisto, the outermost of Jupiter's 4 large moons, measures 2,995 miles in diameter, the third largest moon in the solar system. Callisto possesses the most heavily cratered surface known, a visual record of 4 billion years of intense bombardment. Unlike the other Galilean moons, Callisto shows no evidence of internal geological activity. It has remained essentially unchanged for billions of years, a frozen museum preserving the violent early history of the solar system. Every crater tells a story of cosmic collision, of rocks and ice hurled across millions of miles of space to impact this distant world. Mercury, the smallest planet in our solar system, measures just 3,032 miles in diameter, barely larger than Jupiter's moons Ganymede and Titan. Here is where our journey takes a strange turn. We've been building up through scales of increasing size, but Mercury reminds us that size alone doesn't determine cosmic importance. Despite being smaller than some moons, Mercury is a planet because it orbits the Sun directly and has cleared its orbital neighborhood of other objects. Mercury's proximity to our star creates the most extreme temperature variations in the solar system, swinging from 750 degrees Fahrenheit on the day side to minus 290 degrees Fahrenheit on the night side, a temperature range of over 1,000 degrees. The planet's huge iron core occupies 85% of its radius, giving Mercury the second highest density in the solar system after Earth. This composition suggests Mercury may be the remnant core of a much larger planet, stripped of its outer layers by early collisions or solar radiation. Mercury completes an orbit around the Sun in just 88 Earth days, but its rotation is extraordinarily slow, taking 59 Earth days to complete one rotation. This creates a bizarre relationship where one Mercury day, from sunrise to sunrise, lasts 176 Earth days. As we contemplate these worlds, moons larger than planets, planets smaller than moons, bodies shaped by gravitational forces so extreme they defy earthly experience, we're approaching the limits of what human intuition can process. Each of these objects could contain mysteries that would occupy scientists for generations. But everything we've discussed so far, from the smallest asteroids to these remarkable moons and small planets, exists within a relatively tiny region of space. We haven't yet ventured into the true vastness that defines our solar system. We're still operating within distances that, while large, remain somewhat comprehensible. That's about to change dramatically as we encounter objects and distances that will force us to completely reconsider what we think we understand about space, scale, and our cosmic neighborhood. Its extreme proximity to the Sun creates surface temperatures that vary between 800 and 6 degrees Fahrenheit during the day and negative 292 degrees Fahrenheit at night. Mercury experiences the greatest temperature variation of any body in the solar system, oscillating 1,098 degrees Fahrenheit daily. Imagine a world where the temperature difference between day and night exceeds the melting point of most metals. Lead would be liquid during Mercury's day and frozen solid at night. Mercury's iron core occupies 85% of the planet's radius, a proportion larger than any other planet in the solar system. This dense composition gives Mercury the second highest density after Earth, despite being the smallest planet. Think about what this means. Mercury is essentially a giant iron ball with a thin rocky shell. Scientists theorize that early in solar system history, Mercury might have been much larger, but intense solar radiation, or a catastrophic collision, stripped away most of its outer rocky layers, leaving behind primarily the dense metallic core. Mercury orbits the Sun at an average distance of 36 million miles, completing an orbit in just 88 Earth days. However, its rotation is extraordinarily slow, taking 59 Earth days to complete one rotation on its axis. This peculiar combination creates one of the strangest day-night cycles in the solar system. One solar day on Mercury, from sunrise to sunrise, lasts 176 Earth days, equivalent to 2 complete Mercurian years. Imagine experiencing 2 full years between consecutive sunrises. But as we venture outward from these inner worlds, we encounter objects that challenge our very definitions of planets and moons. Titan, Saturn's largest moon, measures 3,200 miles in diameter, larger than Mercury, and possesses the only dense atmosphere of any natural satellite in the solar system. Surface pressure on Titan is 1.5 times Earth's atmospheric pressure. Titan represents perhaps the most Earth-like world we've discovered, yet it's utterly alien. Lakes and rivers of liquid methane cover its surface, the only other location in the solar system with stable surface liquids besides Earth. The surface temperature hovers at negative 290 degrees Fahrenheit, cold enough to keep methane liquid. Picture this alien hydrological cycle. Methane evaporates from lakes, forms clouds, and rains back down as methane precipitation. Titan has weather systems, erosion patterns, and seasonal changes, all driven by methane instead of water. It's like a distorted mirror of Earth, showing us what planetary dynamics might look like under completely different chemical conditions. Ganymede, the largest moon in the entire solar system, measures 3,273 miles in diameter, surpassing Mercury in size, but not in mass. Ganymede is the only natural satellite known to possess its own magnetic field, indicating a liquid metallic core. Despite its impressive size, Ganymede contains vast amounts of water ice, making its density roughly half that of Earth. This moon is essentially a giant dirty snowball with a metallic heart, a world where ice behaves like rock and liquid water exists in hidden oceans beneath frozen surfaces. Mars measures 4,212 miles in diameter, approximately half Earth's size, with a mass of only 11% of our planet. Martian gravity is 38% of Earth's, where a 150-pound person would weigh just 57 pounds. This reduced gravity enables geological features impossible on Earth. Olympus Mons, Mars's largest volcano, rises 13.5 miles high, 2.5 times taller than Mount Everest. This height is possible because Martian gravity is too weak to collapse such massive structures under their own weight. The Valles Marineris Canyon system stretches 2,500 miles across Mars's surface, 10 times longer than the Grand Canyon. If this canyon existed on Earth, it would span the entire United States from coast to coast. Mars possesses two permanent polar ice caps composed of water ice and frozen carbon dioxide, expanding and contracting with the planet's seasons. The Martian atmosphere is only 0.6% of Earth's atmospheric pressure, so thin that liquid water evaporates instantly on the surface. Yet geological evidence indicates Mars possessed liquid oceans 3.8 billion years ago, when its atmosphere was much denser. Ancient riverbeds, lake deposits, and mineral formations that require liquid water tell the story of a world that once resembled early Earth. Mars orbits the Sun at an average distance of 141.5 million miles, taking 687 Earth days to complete one orbit. During opposition, when Earth and Mars are closest, the red planet approaches within 35 million miles of us. During conjunction, when Mars is on the opposite side of the Sun, it can be over 240 million miles away. But as we venture beyond Mars, we enter a realm populated by objects that exist at the very edge of planetary classification. Eris possesses 27% more mass than Pluto, but a slightly smaller diameter of 1,445 miles due to its denser composition. Eris orbits so far from the Sun that it takes 558 Earth years to complete one orbit around our star. At Eris's average distance of 68 astronomical units, the Sun appears as merely a bright star, providing 1/40th of 1% of the illumination Earth receives. Temperatures on Eris hover around -400 degrees Fahrenheit, so cold that nitrogen freezes solid. Makemake, another Kuiper Belt dwarf planet, measures 888 miles in diameter, its surface covered by brilliant frozen methane. The methane ice gives Makemake one of the highest reflectivities in the solar system. It shines like a cosmic mirror in the outer darkness. Haumea presents an extremely elongated shape, measuring 1,436 by 1,056 miles, due to ultra-rapid rotation of 3.9 hours. This rotation flattened the celestial body into a cosmic rugby ball shape, the only object of its kind known in the solar system. Imagine a world spinning so fast that centrifugal force stretches it into an oval. Haumea's day lasts less than 4 hours, meaning you could watch the sun rise and set 6 times in a single Earth day. The gravitational forces at Haumea's equator would feel significantly weaker than at its poles due to the rapid rotation. Kuiper Belt objects orbit between 30 and 50 astronomical units from the Sun, a region inhabited by hundreds of thousands of icy bodies. The Kuiper Belt probably contains 100,000 objects larger than 62 miles in diameter, awaiting future detailed discovery. Each of these distant worlds preserves the original chemistry of the solar nebula, frozen in time for 4.6 billion years. They're cosmic fossils, unchanged since the solar system's birth, holding secrets about planetary formation that we're only beginning to understand. The Kuiper Belt represents our first encounter with truly vast distances. When we say 30 to 50 astronomical units, we're describing a region that extends from about 2.8 billion miles to 4.6 billion miles from the Sun. To put this in perspective, light from the Sun takes 4 to 7 hours to reach these distant objects. Radio signals from spacecraft exploring the Kuiper Belt take the same amount of time to reach Earth. A conversation with a hypothetical astronaut in the Kuiper Belt would involve 8 to 14-hour delays between question and answer. Yet, even these enormous distances, spanning billions of miles, represent just the beginning of our solar system's true scale. The Kuiper Belt, vast as it seems, occupies only the inner suburbs of our cosmic neighborhood. As we've journeyed outward from microscopic quarks to these distant icy worlds, we've covered an almost incomprehensible range of scales, from particles measuring 10 to the -18th meters to dwarf planets orbiting billions of miles from the Sun. We've traversed more than 30 orders of magnitude. But here's what should truly astound you. Everything we've discussed so far, every planet, moon, asteroid, and Kuiper Belt object, exists within a tiny fraction of our solar system's actual boundaries. The gravitational influence of our Sun extends far beyond these distant dwarf planets, reaching into regions so vast that they begin to approach interstellar distances. We're about to discover that our local neighborhood is incomparably larger than anything we've imagined, stretching toward the very limits of what can still be called part of our solar system. The journey into true cosmic vastness is just beginning. These frozen worlds preserve the original chemistry of the solar nebula, unchanged for 4.6 billion years without alteration. Comets are icy bodies originating from these most distant and cold regions of the solar system beyond Neptune's orbit. But before we venture into those truly remote realms, we need to understand the scale of the worlds closer to home, worlds that will serve as stepping stones to help us grasp the incomprehensible distances ahead. Venus possesses a diameter of 7,521 miles, only 404 miles smaller than Earth, earning the nickname Sister Planet. However, its carbon dioxide atmosphere creates a runaway greenhouse effect, elevating surface temperature to 867 degrees Fahrenheit constantly. This is hot enough to melt lead, zinc, and tin. No spacecraft has survived more than a few hours on Venus's surface before being destroyed by the extreme conditions. The Venusian atmospheric pressure is 92 times Earth's pressure at sea level, equivalent to oceanic pressure at 3,000 feet depth. This crushing pressure would collapse terrestrial submarines like aluminum cans in seconds. Imagine trying to walk on Venus. The atmospheric pressure alone would be like having the weight of a mile-deep ocean, pressing down on every square inch of your body. Add the temperature hot enough to melt metal, and you begin to understand why Venus represents one of the most hostile environments in the solar system. Venus rotates in retrograde direction, opposite to all other planets, taking 243 Earth days to complete one rotation. However, its orbit around the Sun takes only 225 days, making one Venusian day longer than one Venusian year. This bizarre relationship means that if you could somehow survive on Venus's surface, you'd experience fewer than 2 sunrises per year. The sun would rise in the west, crawl slowly across the sky for months, then set in the east after more than 100 Earth days. The Venusian atmosphere is so dense it distributes heat uniformly, making poles and equator have practically identical temperatures. Sulfuric acid clouds permanently cover the planet, reflecting 75% of sunlight and making the surface invisible from space. Despite infernal surface conditions, altitudes between 31 and 37 miles have temperature and pressure similar to Earth. Some scientists have proposed floating cities at these altitudes as humanity's first permanent settlement on another planet. Venus orbits the Sun at an average distance of 67 million miles, receiving nearly twice the solar radiation that Earth receives. Earth measures 7,918 miles in equatorial diameter, establishing the reference scale for rocky planets throughout the solar system. Its equatorial circumference extends 24,901 miles. A distance light crosses in 0.13 seconds. Earth's volume reaches 260 trillion cubic miles, sufficient to contain 1.3 million spheres the size of Ceres. Our planet's mass totals 13 sextillion 170 quintillion pounds, a number equivalent to 6, followed by 24 zeros. If we could place Earth on a cosmic scale, we'd need 81 moons to balance its total weight. Earth's surface gravity accelerates objects at 32 feet per second squared, meaning after 1 second of free fall, a dropped object reaches 22 miles per hour. Earth's atmosphere extends to 6,200 miles altitude, though 75% of air concentrates within the first 6.8 miles. This gaseous layer represents only 0.01% of Earth's total mass, proportionally thinner than an apple's skin. Earth's oceans cover 71% of the surface and contain 333 million cubic miles of salt water. All this water represents only 0.02% of Earth's mass, a thin film on the surface of a massive rocky sphere. The iron-nickel core measures 2,165 miles in radius, hotter than the Sun's surface at 9,700 degrees Fahrenheit. This molten metal heart generates Earth's magnetic field, protecting us from deadly solar radiation. Earth orbits the Sun at an average velocity of 66,600 miles per hour constantly. At this speed, Earth traverses its own diameter in just 7 minutes of continuous orbital motion. One complete orbit around the Sun measures 584 million miles, traveled in exactly 365.256 days. Earth's rotation completes in 23 hours, 56 minutes, and 4 seconds, slightly less than a mean solar day. At the equator, Earth's surface moves at 1,038 miles per hour, due solely to planetary rotation. At the poles, rotational velocity drops to 0, creating a difference of over 1,000 miles per hour between equator and poles. Despite these tremendous velocities, we feel no motion due to inertia. Earth drags its atmosphere, oceans, and all life along as an integrated system, moving through the void. But even Earth, our reference point for everything we consider large and substantial, becomes almost insignificant when we consider the true giants of our solar system. We've been building upward through scales of increasing size, from subatomic particles to planets thousands of miles across. Each step has challenged our intuitive understanding of scale, but we're approaching objects so massive that they dwarf everything we've discussed so far. The gas giants of our outer solar system operate on scales that begin to approach the truly incomprehensible. When we examine Jupiter, Saturn, Uranus, and Neptune, we encounter worlds so vast that they could contain dozens or hundreds of Earths. These giants mark our transition from objects we can still somewhat comprehend to scales that start breaking down human intuition entirely. A single storm on Jupiter exceeds Earth's diameter. Saturn's rings span a distance greater than the Earth-Moon separation. But even these colossal planets pale in comparison to our Sun, the star that dominates our solar system so completely that it contains 99.86% of all mass within trillions of miles. As we prepare to encounter these cosmic behemoths, remember that everything we've covered so far, from the smallest particles to the largest planets, exists within a gravitational system controlled by a single star. The Sun's influence extends far beyond the orbit of Neptune, reaching into regions so distant that our fastest spacecraft take decades just to approach their boundaries. We're about to discover that our solar system isn't just large in the way that planets are large compared to people. It's large in a way that completely transcends human experience and evolutionary understanding. The scale we're approaching will force us to confront the limitations of our own cognition, to recognize that some aspects of physical reality exceed not just our daily experience, but the very capacity of human brains to process spatial relationships. We stand at the threshold of encountering cosmic scales that will challenge everything we think we understand about size, distance, and our place in the universe. Despite these tremendous velocities, we don't feel the movement due to the physical principle of inertia discovered by Galileo and Newton. Earth drags along its atmosphere, oceans, and all life, moving as an integrated system through empty space. Now we encounter the true giants of our solar system, worlds so vast they operate by entirely different physical rules than the rocky planets we've explored. Uranus measures 31,518 miles in diameter, 4 times Earth's size, classified as an ice giant due to its chemical composition. But Uranus has a peculiarity that makes it unique among all planets. It rotates on its side with an axial tilt of 98 degrees. This extreme tilt probably results from a colossal planetary collision in the primordial solar system. Imagine the violence required to knock an entire world onto its side. An impact so catastrophic, it fundamentally altered the planet's orientation forever. Scientists believe this collision occurred early in solar system history, when planetary formation was still chaotic and violent. A Mars-sized object traveling at tens of thousands of miles per hour slammed into the proto-Uranus with enough energy to tilt the entire planet. The impact was so severe it likely melted both objects temporarily, reshaping Uranus's interior structure and creating a tilted magnetic field that doesn't align with either the rotational or orbital axes. This bizarre tilt creates the strangest seasonal cycle in the solar system. Each pole receives 42 years of continuous sunlight followed by 42 years of total darkness. During Uranian solstice, one pole points directly at the sun, while the other plunges into polar night, lasting decades. Picture living on Uranus during this eternal winter. For 42 years, longer than most human lifetimes, an entire hemisphere would never see sunrise. Children would be born, grow to adulthood, and reach middle age without ever experiencing daylight. The psychological effects would be unimaginable. Even Antarctica's winter night, lasting only a few months, challenges human mental health. The transition between seasons on Uranus spans decades. As the planet moves through its 84-year orbit, the terminator, the boundary between day and night, creeps across the surface at a pace measured in years. Regions experience gradually lengthening or shortening days spanning human generations. Uranus completes one rotation in 17 hours and 14 minutes, but its orbit around the Sun takes 84 complete Earth years. Despite being classified as an ice giant, Uranus still contains 80% of its mass in gaseous hydrogen and helium. The ice giant classification refers not to surface conditions, but to the planet's composition. Beneath the hydrogen-helium atmosphere lies a mantle of water, methane, and ammonia ices under such extreme pressure they behave like hot, dense fluids. These materials remain liquid at temperatures that would freeze them solid under Earth conditions, compressed by the weight of the entire planetary atmosphere above. Only 20% of Uranian mass consists of heavier elements like methane, ammonia, and water, in deep internal layers. The atmosphere contains methane that absorbs red light, giving the planet its characteristic blue-green color. This methane absorption creates one of the most distinctive planetary appearances in the solar system. While Jupiter and Saturn display complex banded patterns in browns, reds, and yellows, Uranus appears as an almost featureless blue-green disk. The atmospheric chemistry essentially filters out red wavelengths, leaving only blues and greens to reflect back to observers. Uranus orbits the Sun at an average distance of 1,784,000,000 miles, 19.2 astronomical units of orbital separation. At this distance, sunlight is 400 times weaker than on Earth, causing atmospheric temperatures to plummet to negative 371 degrees Fahrenheit. At such distances from our star, the Sun appears as merely a bright point of light, providing insufficient energy to drive our weather systems. Yet Uranus still experiences atmospheric dynamics powered by internal heat left over from the planet's formation. Interestingly, Uranus radiates almost no excess heat compared to the energy it receives from the Sun. This distinguishes it from other giant planets, which all emit significantly more energy than they receive. Scientists theorize the ancient collision that tilted Uranus may have also disrupted its internal heat sources, causing the planet to cool more rapidly than its siblings. Neptune, the most distant planet, measures 31,000 miles in diameter, slightly smaller than Uranus, but significantly more massive due to higher density. Neptune contains 17 times Earth's mass, while Uranus contains only 14.5 times Earth's mass, despite their similar sizes. This density difference reveals fundamental distinctions in planetary composition and formation history. Neptune's greater density suggests it contains more rocky and icy material in proportion to hydrogen and helium gas. The two ice giants likely formed in different regions of the primordial solar system before migrating to their current positions. Neptunian winds reach 1,300 miles per hour, the fastest in the entire solar system, despite Neptune's extreme distance from the Sun. These supersonic winds are powered by the planet's internal heat source, which radiates 2.6 times more energy than Neptune receives from solar radiation. Think about this paradox. Neptune orbits so far from the Sun that solar heating is virtually negligible, yet it generates powerful atmospheric dynamics from internal energy sources. The planet is essentially a self-heating world, powered by gravitational compression and radioactive decay in its core. The wind speeds on Neptune exceed those of any known hurricane or tornado on Earth. These storms aren't temporary weather events. They're permanent features of a planetary atmosphere operating under completely alien physical conditions. The thin atmosphere and lack of solid surface allow winds to achieve velocities that would be impossible on terrestrial worlds. Neptune possesses a great dark spot, a storm system the size of Earth that appears and disappears approximately every decade. Unlike Jupiter's great red spot, which has persisted for centuries, Neptune's atmospheric features prove more transient, appearing and vanishing on timescales of years to decades. The Neptunian atmosphere is more dynamic than Uranus's, featuring bright methane clouds at high altitudes. These clouds form when methane gas rises high enough to condense into ice crystals, creating brilliant white features against the deep blue atmospheric background. Neptune orbits at 2,795,000,000 miles from the Sun, 30 astronomical units, where sunlight is 900 times weaker than on Earth. At this distance, the Sun appears as an exceptionally bright star, but not as a perceptible disk to the naked eye. To put this in perspective, if you were standing on Neptune, the Sun would appear smaller than Venus does from Earth. The solar disk would be barely distinguishable from a bright star, providing less illumination than Earth receives from the full moon. Neptune takes 164.8 Earth years to complete one solar orbit. Discovered in 1846 through mathematical predictions rather than direct observation, Neptune completed its first observed orbit in 2011. Anyone alive during Neptune's discovery never lived to see it complete one full journey around the Sun. The discovery of Neptune represents one of the greatest triumphs of theoretical astronomy. Urbain Le Verrier calculated the planet's position based solely on gravitational perturbations of Uranus's orbit. When astronomers pointed their telescopes at Le Verrier's predicted coordinates, they found Neptune within 1 degree of the calculated position. Neptune completes one rotation in 16 hours and 6 minutes, faster than Earth despite being 4 times larger in diameter. This rapid rotation contributes to the extreme wind speeds by creating powerful Coriolis effects that organize atmospheric circulation into high-velocity jet streams. But even Neptune pales before Saturn, the second largest planet in our solar system. Saturn measures 72,367 miles in diameter, 9.4 times larger than Earth. Saturn's average density is only 43 pounds per cubic foot, less dense than water. If a sufficiently large ocean existed, Saturn would float. This fact never fails to astound people. A planet larger than 700 Earths would bob on the surface of a cosmic ocean like a cork. This extraordinarily low density results from predominantly gaseous composition, 96% hydrogen and helium with traces of other elements. Saturn contains 95 times Earth's mass, but due to its low density, its volume could contain 764 Earths. Saturn's rings extend 175,000 miles in diameter, but measure only 33 to 328 feet in vertical thickness. Proportionally, the rings are thinner than a sheet of paper on a scale comparable to a football field. These rings contain trillions of ice particles ranging from microscopic grains to mountain-sized blocks. The total mass of Saturn's rings equals only 0.00002% of Saturn's mass, an incredibly delicate and extensive structure. Imagine standing on Saturn's equator and looking up at the rings. They would arc across the entire sky like a brilliant bridge of light, casting complex shadows on the planet's surface as they block sunlight at different angles. The rings would be so wide that their apparent size would exceed the width of your outstretched hand, stretching from horizon to horizon. The rings aren't solid structures, but countless individual particles following separate orbits. Each piece of ice and rock obeys Kepler's laws independently, creating waves, gaps, and resonance patterns as gravitational forces from Saturn's moons sculpt the ring system. Ring particles range in size from dust grains to house-sized boulders, all orbiting Saturn at different speeds depending on their distance from the planet. Inner ring particles complete orbits in 7 hours, while outer particles take 14 hours. This differential rotation creates the complex structure we observe, with gaps maintained by gravitational resonances with Saturn's many moons. Saturn completes one rotation in 10 hours and 33 minutes, generating equatorial winds of 1,100 miles per hour. The rapid rotation creates a persistent hexagonal storm at the North Pole, each side of the hexagon measuring 8,560 miles. This geometric storm pattern has remained stable for decades, representing atmospheric dynamics unlike anything on Earth. The hexagon is large enough that 4 Earths could fit inside it, yet it maintains perfect geometric symmetry year after year. The hexagon represents one of the most mysterious atmospheric phenomena in the solar system. No other planet displays such geometric precision in its weather patterns. The storm maintains 6 perfectly straight sides meeting at precise angles, defying our understanding of fluid dynamics on planetary scales. Saturn orbits the Sun at 886 million miles distance, taking 29.5 Earth years to complete one orbit. Sunlight takes 80 minutes to reach Saturn, compared to 8 minutes to reach Earth. But Saturn, vast as it is, represents only a warm-up for the true giant of our solar system. Everything we've discussed, all the planets, moons, asteroids, and rings, exists within the gravitational domain of a single star so massive it defies comprehension. Our Sun contains 99.86% of all mass within trillions of miles. The combined mass of every planet, moon, asteroid, and comet in the solar system equals less than 0.2% of our star's mass. We're about to encounter an object so colossal that it fundamentally changes the scale of everything we've been discussing. The Sun doesn't just dominate our solar system, it creates and defines it through gravitational forces that extend far beyond anything we've yet explored. Orbital resonances with Saturn's moons create gaps in the rings, such as the Cassini division, measuring 2,981 miles wide. This gap, wide enough to fit the entire continental United States, appears as an empty band separating Saturn's main ring systems. It's maintained by gravitational resonances with the moon Mimas, whose orbital period creates a zone where ring particles can't maintain stable orbits. The precision of this celestial mechanics is staggering. Invisible gravitational forces sculpting ring structure across hundreds of thousands of miles of space. Saturn completes rotation in 10 hours and 33 minutes, generating equatorial winds of 1,118 miles per hour. Hexagonal storms persist at Saturn's North Pole, each side of the hexagon measuring 8,578 miles in length. This geometric storm structure has remained stable for decades, an atmospheric phenomenon never observed on any other known planet. The hexagon is so large that 4 Earths could fit inside it, yet it maintains perfect geometric precision year after year. How atmospheric dynamics create and maintain such geometric perfection remains one of planetary science's greatest mysteries. Saturn orbits the Sun at an average distance of 888 million miles, taking 29.5 Earth years to complete one orbit. Sunlight takes 80 minutes to reach Saturn, compared to 8 minutes to reach Earth. But now we encounter the undisputed king of planets, Jupiter, a world so massive it dwarfs everything we've discussed. Jupiter dominates the solar system with a diameter of 86,881 miles, 11 times larger than Earth in linear dimension. Its volume could contain 1,321 Earths, but its mass is only 318 times Earth's due to low gaseous density. If Jupiter were a basketball, Earth would be smaller than a peppercorn rolling around it in orbit. This comparison captures not just the size difference, but the fundamental dominance Jupiter exercises over the outer solar system. Jupiter contains more mass than all other planets, moons, asteroids, and comets in the solar system combined. Its gravitational influence shapes the orbits of countless objects, from nearby asteroids to distant comets in the outer reaches of the solar system. The planet's composition is 90% hydrogen and 10% helium, similar to the Sun's composition, but insufficient for nuclear fusion. Jupiter represents what astronomers call a failed star. It contains stellar materials, but lacks the mass necessary to ignite fusion reactions in its core. The Great Red Spot of Jupiter is a persistent hurricane that has raged for at least 400 years of continuous astronomical observation, This storm measures 10,160 by 8,090 miles, large enough to swallow two Earths side by side completely. Winds in this tempest reach 422 miles per hour, 3 times faster than the most violent hurricanes on Earth. The storm has persisted longer than European civilization has existed in the Americas, a weather system spanning centuries of human history. Jupiter completes rotation in just 9 hours and 55 minutes, the fastest rotation of all planets in the solar system. This rapid spin flattens the planet, making its equatorial diameter 6.9% larger than its polar diameter. The Jovian atmosphere extends thousands of miles deep, gradually transitioning to liquid metallic hydrogen under extreme compression. Pressures in Jupiter's interior reach 2 million Earth atmospheres, sufficient to transform hydrogen into an exotic conducting metal that doesn't exist naturally anywhere on Earth. This metallic hydrogen creates Jupiter's powerful magnetic field and gives the planet its internal heat source. The pressure required to create metallic hydrogen exceeds anything achievable in terrestrial laboratories, making Jupiter a natural physics experiment operating at scales impossible to replicate on Earth. Jupiter radiates 1.6 times more thermal energy than it receives from the Sun, a remnant of gravitational heat from the planet's formation 4.5 billion years ago. The planet is still slowly contracting and releasing energy from its initial collapse. If Jupiter were 80 times more massive, thermonuclear ignitions would begin in its core, transforming it into a brown dwarf star. Our solar system came remarkably close to being a binary star system, with potentially catastrophic consequences for planetary formation and the possibility of life. Jupiter's magnetosphere extends over 4 million miles, larger than the Sun itself, representing the most powerful magnetic field environment in the solar system. This magnetosphere captures solar particles in radiation belts so intense they would destroy unprotected satellites within hours. The radiation environment around Jupiter exceeds that found in nuclear reactors. Spacecraft visiting the Jovian system require special shielding to survive, and even with protection, their electronics suffer degradation from the intense radioactive bombardment. Jupiter orbits the Sun at an average distance of 484 million miles, 5.2 astronomical units of orbital separation. Gravity at Jupiter's visible surface is 2.5 times Earth's, where a 150-pound person would weigh 375 pounds. But Jupiter, colossal as it appears, shrinks to insignificance when compared to our Sun, the star that creates and controls everything we've been discussing. The Sun measures 865,000 miles in diameter, 109 times larger than Earth in linear dimension. Its volume could contain 1.3 million Earths, a massive sphere gravitationally dominating everything within trillions of miles. Let me help you visualize this scale. If Earth were a grape, the Sun would be a sphere 8 feet in diameter. If Earth were a ping-pong ball, the Sun would be 15 feet across. No matter what comparison we use, the Sun dwarfs Earth to an almost incomprehensible degree. Solar mass totals 4.4 nonillion pounds, representing 99.86% of all mass in the entire solar system combined. Jupiter, the largest planet, contains only 0.1% of the Sun's mass. All planets together comprise merely 0.14% of the total. These numbers reveal the fundamental structure of our solar system. It's not a collection of objects orbiting in space. It's a single massive star with tiny debris scattered around it at enormous distances. If the Sun were a basketball measuring 9.5 inches, Earth would be a peppercorn measuring less than 1/10 of an inch, orbiting 85 feet away. On this same scale, Jupiter would be a marble measuring 1 inch across, orbiting 460 feet from the Sun. Neptune, the most distant planet, would orbit half a mile away on this scale, farther than you could clearly see the basketball representing our Sun. The scale of even the planetary solar system exceeds human intuitive understanding. The Sun's core reaches temperatures of 27 million degrees Fahrenheit and pressures of 250 billion Earth atmospheres. Under these extreme conditions, nuclear fusion converts 600 million tons of hydrogen into helium every second. This fusion process releases energy equivalent to 100 billion hydrogen bombs exploding simultaneously every second without interruption. The energy generated in the solar core takes between 100,000 and 170,000 years to reach the surface due to constant scattering by dense solar material. Surface temperature of the Sun reaches 9,980 degrees Fahrenheit, hot enough to vaporize any known material instantly. Solar gravity at the surface is 28 times Earth's gravity, where a 150-pound person would weigh 4,200 pounds. This immense gravitational field holds the entire solar system together, maintaining planetary orbits across billions of miles. The Sun's gravitational influence extends far beyond Neptune, reaching toward the very boundaries of interstellar space. But even our Sun, massive beyond human comprehension, represents just one ordinary star among hundreds of billions in our galaxy. The true scale of our cosmic neighborhood extends far beyond anything we've yet imagined. As we prepare to explore the outer boundaries of the solar system, we're approaching distances so vast they begin to merge with interstellar space itself. The journey from familiar planetary scales to the true edges of our solar system will challenge every assumption we hold about cosmic distances and our place in the universe. Neptune, the most distant planet, would orbit half a mile away on this scale, beyond any complete football field available. The solar core measures 93,000 miles in radius, where temperature reaches 27 million degrees Fahrenheit and pressure exceeds 250 billion Earth atmospheres. Under these extreme conditions, nuclear fusion converts 600 million tons of hydrogen into helium every second. This fusion releases energy equivalent to 100 billion hydrogen bombs exploding simultaneously every second without interruption. Try to wrap your mind around that number. Every single second, our Sun generates more energy than humanity has produced throughout our entire history, and it's been doing this for 4.5 billion years without pause. The energy generated in the solar core takes between 100,000 and 170,000 years to reach the solar surface due to constant scattering by dense solar material. A photon created in the Sun's core today began its journey during the last ice age on Earth. Think about this incredible journey. Light particles created when mammoths roamed the Earth are only now emerging from the Sun's surface to begin their 8-minute journey to your eyes. The light you see when you look at the Sun carries energy that predates human civilization by hundreds of centuries. The photosphere, the Sun's visible surface, maintains a temperature of 9,980 degrees Fahrenheit, emitting light that traverses the entire solar system. Sunspots appear as dark regions, but actually reach temperatures of 6,880 degrees Fahrenheit, hotter than terrestrial iron foundries. The largest sunspot ever recorded measured 99,400 miles in diameter, sufficient to swallow 12 Earths arranged horizontally. These dark regions on the Sun's surface would instantly vaporize our entire planet, yet they appear cool compared to the surrounding photosphere. The solar corona, the Sun's external atmosphere, extends millions of miles with a paradoxical temperature of 3.6 million degrees Fahrenheit. This represents one of astronomy's greatest mysteries. How does the Sun's atmosphere become hundreds of times hotter than its surface? Solar flares release energy equivalent to 10 million nuclear bombs, launching plasma at velocities of 621 miles per second. These eruptions can disrupt satellite communications, damage power grids, and create auroras visible as far south as the Caribbean. Surface gravity on the Sun is 28 times Earth's gravity, where a 150-pound person would weigh 4,200 pounds. This immense gravitational field maintains the entire solar system in orbit, exerting dominant influence to distances of 2 light-years from the solar center. A light-year represents the distance light travels in 1 year, approximately 5.8 trillion miles of spatial extension. To put this in perspective, Neptune orbits at only 0.0005 light-years from the Sun, a minuscule fraction of the Sun's true sphere of gravitational influence. The Sun loses 4 million tons of mass every second due to mass-energy conversion described by Einstein's equation E=mc2. Despite this tremendous loss, the Sun will continue fusing hydrogen for another 5 billion years before exhausting its nuclear fuel. When that happens, the Sun will expand into a red giant star, its radius growing until it engulfs Mercury, Venus, and possibly Earth. In this phase, the Sun will measure 155 million miles in diameter, reaching beyond Mars's current orbit in the solar system. But the Sun's influence extends far beyond electromagnetic radiation and gravitational pull. The solar wind, a constant stream of charged particles, travels at velocities between 186 and 497 miles per second, streaming away from the Sun in all directions. This wind creates a magnetic bubble called the heliosphere, a structure extending far beyond the orbit of all known planets. The heliosphere protects the solar system from galactic cosmic rays, interstellar radiation that would damage DNA and electronics without this protection. Earth's atmosphere and magnetic field provide additional shielding, but the heliosphere represents our first line of defense against cosmic radiation. The Voyager 1 and 2 probes crossed the heliosphere's boundary in 2012 and 2018, respectively, becoming the first human-made objects to enter interstellar space. Voyager 1 was 11.7 billion miles from the Sun when it crossed this frontier, 125 times the Earth-Sun distance. Radio signals from the Voyagers take over 20 hours to reach Earth, traveling at light speed through empty space. Communication with these distant explorers involves delays, longer than most people's waking hours, making real-time control impossible. The heliopause, the boundary where solar wind meets the interstellar medium, lies approximately 120 astronomical units from the Sun. However, the Sun's gravitational influence extends far beyond the heliosphere into a region called the vast Oort cloud. The Oort cloud represents a spherical shell of trillions of frozen comets orbiting the Sun at distances unimaginable to human minds. This region begins approximately 2,000 astronomical units from the Sun, about 186 billion miles of radial distance. For comparison, Neptune orbits at only 30 astronomical units, meaning the Oort cloud begins 67 times farther than Neptune's orbit. If Neptune's distance represents a journey to the next town, the Oort cloud begins at distances equivalent to traveling to other continents. The Oort cloud extends possibly to 100,000 astronomical units, approximately 1.6 light-years from the central Sun. At this extreme distance, our Sun appears merely as an exceptionally bright star, indistinguishable from other stars to the naked eye. Light from the Sun takes over 1 complete year to reach the outer regions of this distant Oort cloud. If the solar system were scaled so the Sun was an orange in the center of a football field, the Oort cloud would extend 4 miles in all directions. Scientists estimate the Oort cloud contains between 1 trillion and 100 trillion comet nuclei, each measuring a few miles in diameter. These objects represent remnants of planetary formation, ejected to extreme orbits by gravitational interactions with the giant planets during the solar system's chaotic early history. Gravitational perturbations from passing stars occasionally deflect comets from the Oort cloud toward the inner solar system, becoming the long-period comets that appear every few thousand years. Comet Hale-Bopp, visible in 1997, originated from these distant reaches and won't return for 2,500 years. The total estimated mass of the Oort cloud equals approximately 5 Earth masses, distributed throughout a volume of space so vast it approaches interstellar dimensions. Individual comets in the cloud are separated from their nearest neighbors by tens of millions of miles of absolute emptiness. The density of objects in the Oort cloud is so low that spacecraft could traverse it without detecting a single object. Yet the cloud's existence is inferred from the quantity and orbital characteristics of long-period comets observed throughout recorded history. The Oort cloud marks the true boundary of our solar system, the limit of the Sun's gravitational control over orbiting objects. Beyond this realm, we enter truly interstellar space, where the nearest star systems begin to exert comparable gravitational influence. Proxima Centauri, our nearest stellar neighbor, lies 4.24 light-years away, approximately 268,000 astronomical units from the Sun. At this distance, Voyager 1 would require 73,000 years to make the journey while maintaining its current velocity. Proxima Centauri is only 2.7 times farther than the outer edge of the Oort cloud, demonstrating that our solar system approaches interstellar dimensions. The boundary between solar and interstellar space is not sharply defined, but represents a gradual transition zone where multiple gravitational influences compete. This reveals something profound about the scale of our cosmic neighborhood. The solar system isn't just the planets we see in textbooks. It's a vast, three-dimensional structure extending more than halfway to the nearest stars. The scale we've explored challenges fundamental assumptions about space and cosmic organization. From subatomic particles to the Oort cloud, we've traversed more than 35 orders of magnitude, a range of scales that completely transcends human evolutionary experience. Our brains evolved to process distances measured in miles, not light-years. We can navigate forests and plains, estimate the distance to mountains, judge the size of animals and objects within our immediate environment. But cosmic scales operate beyond anything our neural architecture was designed to comprehend. The solar system reveals itself as a structure dominated by emptiness on scales that defy intuitive understanding. The space between objects isn't merely large, it's empty in ways that have no earthly equivalent. The vacuum between planets exceeds any vacuum achievable in terrestrial laboratories. Yet this apparently empty space teems with invisible activity: solar wind, magnetic fields, gravitational waves, cosmic radiation, and the subtle gravitational influences that maintain planetary orbits across billions of miles. We exist within this vast cosmic architecture without any direct sensory awareness of its true scale. Earth seems substantial and permanent to us, but it represents less than a grain of dust in the cosmic structure that houses us. The journey from quarks to the Oort cloud encompasses everything humans have ever experienced or can hope to directly explore. Yet even this enormous range, spanning the very small to the unimaginably vast, represents just our immediate cosmic neighborhood in a universe containing hundreds of billions of similar star systems. At this extreme distance, the Sun would appear merely as a bright star, indistinguishable from other stars to the naked eye. Sunlight takes more than one complete year to reach the outermost regions of the distant Oort cloud. Think about that for a moment. Light that left the Sun when you were celebrating your last birthday is only now arriving at the very edge of our solar system's gravitational domain. If the solar system were scaled down so the Sun was an orange in the center of a football field, the Oort cloud would extend nearly 4 miles in all directions. This scaling exercise reveals the true nature of our cosmic neighborhood. What we typically think of as the solar system, the planets, moons, and asteroid belt, would fit within the 50-yard line of that football field. Everything else, extending for miles in every direction, represents the vast, nearly empty realm that truly defines our solar system's boundaries. Scientists estimate the Oort cloud contains between 1 trillion and 100 trillion cometary nuclei, each measuring a few miles in diameter. These comets are remnants of planetary formation, ejected to extreme orbits by gravitational interactions with primordial giant planets. Picture the chaotic early solar system 4.5 billion years ago. Jupiter, Saturn, Uranus, and Neptune were migrating through the planetary disk, their massive gravitational fields flinging countless icy objects outward. Most of these objects were ejected completely from the solar system, but some settled into the distant spherical shell we now call the Oort cloud. Gravitational perturbations from passing stars occasionally deflect comets from the cloud toward the inner solar system, becoming long-period comets. Comet Hale-Bopp, visible in 1997, had an orbital period of 2,530 years, originating from the depths of the outer Oort cloud. Hale-Bopp's journey illustrates the incredible scales involved. This comet spent millennia traveling from the outer reaches of the solar system, gradually accelerating as the sun's gravity pulled it inward. For most of its orbital period, Hale-Bopp was invisible, a frozen chunk of ice and rock drifting in the cosmic deep. When Hale-Bopp finally approached the inner solar system, solar radiation heated its surface, creating the magnificent tail that made it visible from Earth. Yet this spectacular display represented only a tiny fraction of the comet's total orbital journey through the vast emptiness beyond Neptune. The estimated total mass of the Oort cloud equals approximately 5 Earth masses, distributed throughout a colossal volume of space. 5 Earth masses sounds substantial until you consider the volume involved. This mass is spread across a sphere with a radius of nearly 2 light-years. If you could somehow gather all the material in the Oort cloud and compress it into a single world, it would be smaller than Earth, yet distributed across a region approaching interstellar dimensions. A typical comet in the cloud is separated from its nearest neighbor by tens of millions of miles of absolute void. The density of objects in the Oort cloud is so low that spacecraft could traverse it without detecting a single object. This emptiness defies human comprehension. We have no earthly equivalent for such vast separations between objects. The distance between comets in the Oort cloud exceeds the distance from Earth to Venus. Imagine if every building on Earth were separated by interplanetary distances. That begins to approximate the spacing of objects in the Oort cloud. However, the existence of the cloud is inferred from the quantity and orbits of long-period comets repeatedly observed by astronomy. We've never directly detected the Oort cloud, yet its presence is revealed by the steady stream of comets that emerge from its depths. This represents one of astronomy's most elegant examples of inference. By carefully tracking comet orbits backward in time, scientists can determine their points of origin. The consistent pattern of these origins defines the Oort cloud's structure and extent, even though individual comets remain far too small and distant to observe directly. The Oort cloud marks the true limit of the solar system, defining the boundary of solar gravitational influence over orbiting objects. This boundary isn't sharply defined like a planetary surface. Instead, it represents the region where the sun's gravitational influence becomes comparable to that of nearby stars. Objects beyond this realm can be perturbed by stellar gravitational fields and potentially captured by other star systems. The nearest star, Proxima Centauri, lies 4.24 light-years away, approximately 268,000 astronomical units from the Sun. At this distance, Voyager 1 would require 73,000 years to reach it while maintaining its current solar escape velocity. 73,000 years. That's longer than modern human civilization has existed. It's 3 times longer than the entire history of written language. The fastest object humanity has ever created would take longer to reach the nearest star than our species has been using agriculture. Proxima Centauri is only 2.7 times farther than the outer limit of the Oort cloud, demonstrating that our solar system is impressively vast. This proximity reveals something startling about cosmic architecture. The boundary of our solar system extends more than 1/3 of the way to the nearest star. What we consider our local cosmic neighborhood actually approaches interstellar dimensions. The scale of the solar system is defined not by the visible planets, but by the apparently empty space that completely surrounds them. This realization fundamentally challenges our conception of cosmic organization. When we picture the solar system, we typically imagine planets orbiting in space. But the planets represent tiny islands of matter in an ocean of emptiness so vast it approaches the distances between stars. If all planets, moons, asteroids, and comets were removed, the volume of the solar system would remain practically unchanged in dimensions. Remove every object we can name: Earth, Jupiter, Saturn's rings, the asteroid belt, every comet and moon, and the solar system's boundaries would shift imperceptibly. The structure is defined by gravitational influence and magnetic fields, not by the material objects we consider important. The space between objects is the dominant characteristic, not the objects themselves, that we consider important to our everyday understanding. This represents perhaps the most humbling realization in our journey through scales. Everything humans have ever seen, touched, or experienced exists within a cosmic structure that is fundamentally defined by emptiness. The average density of the solar system out to Neptune's orbit is approximately 1 atom per cubic inch of volume. This is 10 trillion times less dense than air at Earth's sea level, a nearly perfect vacuum by terrestrial standards. Including the Oort cloud, the average density drops to levels approaching absolute intergalactic vacuum measured in the remotest regions of the universe. At this point, our solar system becomes virtually indistinguishable from empty space. The matter we think of as substantial, planets, moons, even the sun itself, becomes statistically negligible when averaged across the true volume of our cosmic neighborhood. The Milky Way contains approximately 400 billion stars, each potentially surrounded by its own planetary system similar to ours. If half these stars possess systems like ours, there would exist 200 billion solar systems in our galaxy alone. Each star system potentially harboring its own collection of worlds, its own Oort cloud, its own cosmic architecture spanning light years. The Milky Way measures 100,000 light-years in diameter, but our solar system occupies only about 3 light-years of spherical space. Proportionally, our entire solar system would represent less than a pixel in a photograph of the complete galaxy at appropriate viewing scale. This scaling reveals our cosmic insignificance with mathematical precision. Everything we've discussed, from quarks to the Oort cloud, exists within a region smaller than a pixel when viewed on galactic scales. The observable universe contains an estimated 2 trillion galaxies, each containing billions of stars and their own unknown planetary systems. On this true cosmic scale, our solar system becomes completely invisible, smaller than an atom compared to the entire Earth in proportion. Yet within this invisible speck, we've discovered scales ranging from subatomic particles to structures approaching interstellar dimensions. The range of scales within our cosmic neighborhood exceeds the range between atoms and planets by orders of magnitude. Sunlight takes 8 minutes and 20 seconds to reach Earth, but 5.5 hours to reach Pluto in the distant solar system. A radio transmission from Earth would take more than 17 hours to reach Voyager 1 in nearby interstellar space currently. If we could travel at light speed, we would require 1 year and 7 months to traverse the entire Oort cloud. These timescales reveal the fundamental barrier to human exploration beyond our immediate planetary neighborhood. Even traveling at the universe's speed limit, the velocity of light itself, crossing our solar system requires more than a year. No conceivable technology could enable humans to physically explore even the boundaries of our own solar system. The human brain evolved to process scales between inches and miles, a range of perhaps 6 orders of magnitude. The solar system encompasses scales from subatomic particles to light years, a range exceeding 30 orders of magnitude. 30 orders of magnitude means multiplying by 1030 consecutive times, a number beyond any concrete analogy or comprehension. This difference in scale is so vast that no analogy or model can adequately capture the complete dimensional reality. When we attempt to understand distances of billions of miles, our brains automatically reduce these numbers to abstract symbols devoid of visceral meaning. The solar system reveals that even our immediate cosmic backyard transcends the fundamental limits of human intuitive understanding. Our evolutionary ancestors never needed to process scales beyond a few miles, constraining our neural architecture to terrestrial distances. Visual areas of the brain process depth to about 300 feet. Beyond that, everything appears equally distant and abstract. Even mathematical concepts fail to transmit the visceral experience of these scales. Numbers become mere symbols without emotional resonance or intuitive meaning. 1 billion miles and 1 trillion miles seem equally distant to human cognition, both beyond the capacity for direct processing. The solar system challenges not just our knowledge, but the fundamental architecture of consciousness itself. The vastness of space between objects is the most important characteristic, not the objects themselves that we can name and categorize. Understanding the true scale of the solar system requires accepting that our intuitive grasp of spatial relationships is fundamentally inadequate for cosmic reality. The void dominates everything. The objects we consider substantial are rare exceptions in an incomprehensible ocean of nearly absolute emptiness. No currently conceivable technology would permit humans to physically explore even the boundaries of our complete solar system. The human brain evolved to handle scales between fractions of inches and miles, an interval of only 6 orders of magnitude. 6 orders of magnitude means multiplying by 10^6 consecutive times, like going from 3 feet to 3 million feet. The solar system encompasses scales from nanometers, atoms, to light years in the Oort cloud, an interval of 27 orders of magnitude. 27 orders of magnitude means multiplying by 1027 consecutive times, a number beyond any concrete analogy possible. Try to picture this range. Start with the width of a human hair, about 3/1000ths of an inch. Now multiply that by 10, then multiply that result by 10 again. Continue this process 27 times. The final number would represent the ratio between atomic scales and the Oort cloud. This scale difference is so vast that no analogy or model can adequately capture the complete dimensional reality. Every comparison we attempt breaks down under the weight of these numbers. If an atom were a marble, the Oort cloud would extend beyond the orbit of nearby stars. If a quark were a grain of sand, the solar system would span galactic distances. No earthly experience provides a reference point for such scales. When we attempt to understand distances of billions of miles, our brains automatically reduce these numbers to empty and abstract symbols. This isn't a failure of education or intelligence. It's a fundamental limitation of neural architecture that evolved for entirely different purposes. Our brains categorize large numbers without meaningful distinction between millions, billions, or trillions when these numbers exceed our experiential range. The solar system reveals that even our immediate cosmic neighborhood completely transcends the capacity for human intuitive comprehension. This transcendence isn't merely about size, it's about the fundamental nature of spatial reality itself. We've discovered that our local cosmic environment operates according to principles that our minds literally cannot process directly. Our evolutionary ancestors never needed to process scales beyond a few miles, limiting cerebral architecture to terrestrial distances. For millions of years of human evolution, the farthest meaningful distance was the horizon, perhaps 10 to 20 miles on clear days from elevated positions. The largest objects were mountains. The smallest were insects or seeds. This narrow range of experience shaped every aspect of how our brains process spatial information. Visual areas of the brain process depth to approximately 300 feet. Beyond that, everything appears equally distant and abstract. This limitation explains why distant mountains appear flat against the sky, why the moon seems smaller than a coin held at arm's length, why astronomical photographs fail to convey the true scale of cosmic objects. Our depth perception simply shuts down at distances beyond immediate survival relevance. Even mathematical concepts fail to transmit the visceral experience of scale. Numbers become mere symbols without emotional resonance. Mathematics can describe these scales with perfect precision, but mathematical description isn't the same as comprehension. We can write 10 to the 27th power without truly grasping what that number represents in physical reality. 1 billion miles and 1 trillion miles seem equally distant to human cognition, both beyond intuitive processing. Once numbers exceed our experiential range, they collapse into the category of very large without meaningful differentiation. Our brains treat the distance to Jupiter the same way they treat the distance to the Oort cloud, as abstract symbols representing farther than we can walk. The solar system isn't just big. It's big in a way that fundamentally challenges how our brains process spatial reality. This represents a crucial distinction. Objects can be large while remaining comprehensible. Mountains, oceans, continents. But the solar system is large in a qualitatively different way that breaks our cognitive machinery entirely. The vastness of space between objects is the most important characteristic, not the objects themselves that we can name. We naturally focus on planets, moons, and asteroids because these represent the only features our minds can grasp. But the solar system's defining characteristic is the emptiness between these objects, emptiness so complete it has no terrestrial equivalent. Truly understanding solar system scale requires accepting that our evolutionary intuition is fundamentally inadequate for this task. This acceptance isn't defeatist, it's liberating. Once we acknowledge the limits of intuitive understanding, we can appreciate the remarkable achievement of mapping cosmic architecture through abstract reasoning and mathematical analysis. Emptiness dominates everything. Solid objects are rare exceptions in an incomprehensible ocean of nearly absolute vacuum. Even this statement fails to capture the reality. The ocean metaphor suggests a medium, water, that would be unimaginably dense compared to interplanetary space. The vacuum between planets exceeds any emptiness we can create or imagine based on earthly experience. Even the Sun, dominating 99.86% of all mass, occupies a minuscule fraction of volume when we include the Oort cloud in our definition. Our star, a sphere large enough to contain over 1 million Earths, becomes a nearly invisible speck when viewed against the true scale of the solar system. If the Oort cloud defined a sphere, the Sun would occupy less volume within it than a grain of sand occupies within the Earth. The average density of the complete solar system is essentially zero, emptier than any vacuum we can create in terrestrial laboratories. This reality challenges our perception that the solar system is full of planets and objects, when in fact it represents nearly absolute emptiness. Our sensory experience of solidity and matter represents a local illusion, not the dominant cosmic reality of void. We live on a tiny island of condensed matter in an ocean of nothingness so vast it approaches infinite emptiness. We, made of atoms that are 99.99999% empty space, orbit a star in a system that's 99.9999999% empty within a galaxy that's even emptier. This recursive emptiness reveals something profound about physical reality itself. At every scale, from atomic to cosmic, emptiness dominates over matter. The illusion of solidity emerges only at the narrow range of scales where human experience operates. Solar system scale isn't merely an astronomical fact, it's a revelation about the fundamentally empty nature of physical reality. This emptiness isn't a deficiency or absence, it's the baseline state of the universe. Matter represents rare temporary concentrations of energy in a cosmos that's overwhelmingly vacant space. The human brain fails to comprehend this not due to intellectual limitation, but because it evolved in a world where such comprehension was never necessary. Our ancestors needed to navigate forests, hunt animals, avoid predators, and find shelter. None of these survival tasks required processing cosmic scales. Natural selection shaped our cognitive architecture for terrestrial problem-solving, not astronomical contemplation. Accepting this failure is the first step toward genuinely appreciating how extraordinary it is to exist on such incomprehensibly vast scales. Once we abandon the expectation of intuitive understanding, we can marvel at our species' achievement in mapping cosmic architecture through pure reasoning. Mathematics and physics allow us to explore realms our senses could never reach. The solar system is too vast for intuition, but remains mathematically describable, demonstrating the power of abstract thought over direct perception. This represents perhaps our greatest intellectual triumph, the ability to comprehend realities that transcend every aspect of our evolutionary heritage. Through telescopes, mathematics, and logical reasoning, we've mapped a cosmic neighborhood that dwarfs anything our ancestors could imagine. Let's recapitulate this incredible journey. Quarks, 10 to the minus 18th meters, the smallest constituents of matter we know, billions of times smaller than atoms. Human cells, 50 micrometers, the basic units of life, visible only under microscopes but containing complex molecular machinery. Human beings, 5.5 feet, our reference scale, the 0 point of direct human perception. Manhattan, 13 miles, a familiar urban island that already challenges our ability to traverse on foot in a single day. The Chelyabinsk asteroid, 66 feet, versus Ceres at 588 miles, showing that space objects range from building-sized to dwarf planets. The Moon, 2,100 miles, our nearest natural satellite, 5 times smaller than Earth, but gravitationally dominant in our sky. Earth, 7,900 miles, our planet seeming enormous, but merely a peppercorn on solar scales. Jupiter, 87,000 miles, a gas giant that could swallow 1,321 Earths, yet still insignificant compared to the Sun. The Sun, 865,000 miles, the star containing 99.86% of all solar system mass, gravitationally dominating everything. The Oort cloud, 1.6 light-years or 9 trillion miles, the true boundary of our solar system, where emptiness dominates absolutely everything. This progression spans scales from the invisibly small to the incomprehensibly vast, each step challenging our understanding of size, distance, and cosmic architecture. We've journeyed through more than 30 orders of magnitude, from particles that exist at the very limits of physical measurement to structures that approach interstellar dimensions. The solar system isn't just our cosmic address. It's a revelation about the nature of space, scale, and the extraordinary emptiness that defines physical reality at the largest scales we can explore. If you're still awake, it's because the content was really good. So take a moment, leave a like, and subscribe to the channel. It helps a lot. And if you want to keep watching, just click on the video that's appearing right now. I'll see you there.